Hello students, in the last session we completed sums that were related to friction and then resolving of forces and those stuff. Okay, so in this session we will do sums that are related to tension in a rope, right? So in the last session also last two sums were related to the tension in the rope. Okay, so same way we will do those kind of sums in this session, fine. And then we will do sums that are related to motion of car on a circular track and those things. Okay, so in this session we will do the next 10 sums. Okay, so from 25 to 30 we'll do 10 sums in this session. Okay, fine. So let's jump into the sum. So the 21st sum is actually a system consists of three masses which are like m1, m2 and m3 connected by a string passing over a pulley p. Okay, so you are having like three masses m1, m2 and m3 connected over by a string and passing over through a pulley. Okay, so then you have a pulley that is attached to the edge of a table, and then you got like another one mass. Okay, fine. The mass m1 hangs freely and m2 and m3 are on rough horizontal table. Okay, so m2 and m3 is actually trying to balance this mass m1 because of the friction that is acting between these two rough surfaces. Fine. So in the previous cases, in the previous sum that we did in the last session, we had like only one mass on the table. In this situation, you just got like two masses. Fine. So if needed, I'll just club these two masses into a single mass. If needed, we will do that way. Okay, so you got like m2 and m3 are on a rough horizontal table. The coefficient of friction is mu, so the friction between these two stuff is actually mu. So if it was in motion, then I'll consider it to be like mu k. Okay, so if like kinetic friction is needed, then I'll just take it as coefficient of kinetic friction. That's it. The pulley is frictionless and of negligible mass. So this pulley is frictionless and then it doesn't have any mass that is considerable. Fine. The downward acceleration of mass m1 is, so what will be the downward acceleration with which it is going to fall? Okay. So obviously, if there wasn't any mass that is attached over here, this m1 will fall down with an acceleration of g because of the gravity it is going to fall. But in this situation you are going to have tension which is going to pull this upwards by the amount that this entire system has been pulled forward. Okay, so that is going to happen obviously, right? So this tension will restrict the fall by certain degree, therefore it will not fall downwards with an acceleration of g, it is going to fall downwards with acceleration that is less when compared to g. Okay, so this stuff has to be understood. You shouldn't have any doubt in this part. So what I'm supposed to find here is the acceleration of this m1 after deducting the tension in the rope. So that is what I need to find. Okay, so now let me do the free body diagram and I'll just put all those free body diagram for these two masses and these two masses, and I'll get the tension that is actually pulling this mass forward because of this mass m1. The same tension will balance this m1 by certain degree. So if I get the tension T, then obviously I'll be able to get the acceleration with which this is going to fall downwards. As usual, what I'm going to do here is they have given one more stuff in the question, which is like assume m1, m2, m3 is equal to m, which means mass m1, m2 and m3, all those three masses are of same mass. Okay, which means it has the same constant mass value. So instead of considering this to be like m2 and m3, I'll just to take it together as a single mass and then I'll consider it to be like 2m mass. Okay, so I'll consider this entire system to be single mass. Okay, so this entire system will be considered as a single mass of 2m. Got it? So if that was the case, let me do the free body diagram for this entire system. Okay, on the table. Okay, so if I do it, what will I get? So I'll have a normal reaction that is acting, so that will be a normal reaction, and same way you will have the acceleration due to gravity. Because of that one, you will have like mg that is acting downwards, that's going to be like 2 mg that will be acting downwards. Fine. Same way, the tension in the rope is going to pull this one towards the left. Okay, in the situation it will pull this one towards the left, so that's going to be like by n, that's going to be the tension in the friction. Okay, so that will be this component. Okay, same way the tension is in will be balanced by the frictional force that is acting between the surface. As this is in motion, you are going to have like kinetic friction, so fk will be acting towards the right. Okay, so this is the free body diagram for the system that is above over here. Is there anything left? Okay, so because of this stuff, obviously this is going to accelerate towards the left with an acceleration of a. Okay, so you are going to have an acceleration that will be towards the left left by an acceleration of a. That's what I'm supposed to find over here also, right? So I think the free body diagram for this setup is done. Then I'll have to look at the hanging mass, which is like m1. Okay, if I do look at that one, what will I get? You will end up having m1g that is going to act downwards. Same way you will have like tension that is going to pull it upwards. So it is not going to fall by the complete effect of the acceleration due to gravity. It is going to be less because of the tension in the rope, right? So what I need to find here is the acceleration a. So how will the acceleration a act in this situation? Is like it will act downwards because this is going to fall downwards. Okay, so now I'm just done with all those free body diagram and everything. Now if I just equate this system, I'll end up getting the answer, right? So first let me do the force balance for the mass m1, which is like hanging. So if I do it for that one, summation of force along the y will be equal to ma minus j cap. Okay, it should be clear. If I put the summation of forces along the y, you'll have like tension in the string that's going to act upwards. Okay, and then minus m1g that's going to act downwards, which will be equal to negative ma, right? It should be clear. What I'm supposed to find here is the acceleration. Therefore, what I will do is I'll just equate the tension, because the tension in this rope is going to be the same for both those system. Okay, so if that was the case, then if I just equate the tension in the string, I'll end up getting the acceleration a. Okay, so the first part is done. Then let me do the force balance for the mass to m. Okay, that is above the table. If I do for that one, you'll have like summation of forces along the x will be equal to m a negative I cap. Okay, no, 2ma, right? So double the mass, you're going to have like 2m that is going to move towards the left with an acceleration of a. Okay, so if I do add those summation of forces along the x, you will have something like this. Tension that is going to act towards the left, so that's going to be like negative t, correct? And then you will have like plus fk, kinetic friction, plus fk, which I'll be able to write it as mu n. So instead of n, I'll substitute like 2mg that will be acting towards the right. And then you are going to have the acceleration of the entire system, that will be like minus 2ma. Okay, same thing that I've written over here. Okay, minus 2ma. All those stuff are done. Okay, so here instead of m1, I'll be able to put it as m itself, because all the masses are just the same thing, right? So I'll just plug it as m itself. M. Okay, now let me do the rearrangement stuff on the first equation and on the second equation with respect to the tension. Therefore, I'll get the acceleration in the main equation. If I do equate those two equations, then I'll end up getting the acceleration, right? If I rearrange it in the first case, you'll have like tension T, which is equal to mg minus ma. So that stuff is done. Then you have got tension T, which will be equal to 2ma plus 2 mu mg. Okay, so now these two things are done. Now if I just equate these two tension, then I'll get the acceleration a, right? So let me equate those two stuff. You will have mg minus ma, which will be equal to 2ma plus 2 mu mg. Okay, let me cancel out all those m. When those stuff gets cancelled out, you will have g minus a, which will be equal to 2a plus 2 mu g. Okay, so if I do the rearrangement thing, I'll get the answer. The stuff that I need to find here is actually the acceleration. Therefore, if I do the rearrangement, you will have like something like this: 3a, which will be equal to 2, 3a, which will be equal to negative of 2 mu g plus g, right? Okay, so if I bring the 3 to the other side, it goes to the denominator, so I'll have like 1 by 3. And then if I do factor this stuff, you will have like g, that will get factored out, and then you will have 1 minus 2 mu. Okay, so the acceleration over here is g 1 minus 2 mu divided by 3, which is like option 3, right? Answer here is option 3. Fine. You should be clear with this sum, right? You shouldn't have any doubt on the sum because we did see the same kind of sum in the last session itself. Okay, same logic, same everything is just the same. Only thing is here they have just given you like two different masses, and what I did is I just combined those two different masses into a single mass, and then I just treated the sum as such as the same way that I did in the last case. We ended up getting the answer, right? You shouldn't have any doubt in the sum. Let's move on to the next one. Next sum is a conveyor belt is moving at a speed of 2 meter per second. Okay, so the belt is actually traveling at a speed of 2 meter per second. That's what they've given over here. A box is gently dropped on it, which means I'm just going to put a box on that belt gently, which means initial velocity with respect to the earth or ground will be like 0. That's how I'm going to drop it on that conveyor belt. Okay, it is just dropped. Fine. The coefficient of friction between them is mu. So the friction between the box surface and the belt surface is actually mu, which is equal to 0.5. Okay. The distance that the box will move relative to the belt before coming to rest on it will be. So how far it is going to move on that belt before coming to rest with respect to the belt that is moving. Okay. So that's what I need to find. So how much distance it is going to move. It will actually move backwards. We will see that one. Okay. So once I draw the diagram, you will get the clear understanding of what I'm telling you. Okay. So here you have got like two rollers, and then I'm just going to attach a conveyor belt to it. So this is how we are just going to have that belt. So this is actually traveling at a speed of 2 meter per second. So that will be the velocity with which this belt is actually traveling. Okay. Now what I'm going to do is I'm just going to drop a box on this conveyor belt. So a box is dropped on this conveyor belt. Okay. It is like gently dropped, which means the velocity of this box with respect to the ground is actually 0. Okay. So with respect to the ground, it is actually 0. But for someone who is looking on this box from the external, I mean like from inside the frame of reference of that conveyor belt. Okay, so let me tell you this fashion. Let's say you are having a guy who is attached to this conveyor belt, and then he is just looking at it, which means he is moving in that conveyor belt with a speed of 2 meter per second, and then he is just looking at this box. Then how will it actually look? So this will actually move opposite to that of the direction of the motion of the conveyor belt, which means I'm just going to drop it gently, and then this wants to be with with the velocity of 0 with respect to the ground. So when the conveyor belt moves forward, this stuff seems to be moving backwards with the same velocity. Okay, so the same logic, right? So I just put a load inside a truck, and in the first case of the fictitious force, I just put a load inside a truck. When the truck was actually moving forward, for someone who is standing inside the truck, it seems that the load was moving backwards, right? It was like exactly opposite. So same thing is going to happen over here. So inside the frame of reference of that conveyor belt, when you look at that object, it seems the object seems to be moving the other way around. Okay, if the conveyor belt was moving forward, then it seems to be moving backwards, right? It should be pretty obvious. You shouldn't have any confusion. So here in this situation, this box will have an initial velocity of negative 2 meter per second. Okay, so whatever result that is happening outside, you are going to have the same effect on the opposite direction. Same intuition, right? And the truck was accelerating forward with an acceleration of 2 meter per second square. In that situation, the box inside was actually moving backwards with the same acceleration. In this situation, I just gently dropped it, which means it didn't have any velocity with respect to the earth. Therefore, when the conveyor belt was moving forward, that object which was placed on that particular position seems to be moving in the opposite direction with the same speed, right? So same intuition and same thinking. This is the only tricky part that you need to know with respect to this sum. Okay, so this box seems to be moving backwards with the speed of 2 meter per second. So that stuff is done. Okay, so randomly, if this wants to move backwards, right? For someone who is looking from the inside, this just randomly wants to move backwards, then obviously that belt will give like friction to oppose the direction of that motion. Okay, so frictional force will act opposite to this direction. Okay, so that will be the kinetic friction that's going to act, because this stuff is in motion with the belt, right? So that will be like kinetic friction that's going to act opposite. Okay, so in this direction, kinetic friction is going to act, and backwards this will move with an velocity of initial velocity of 2 meter per second. Then after some time, what will happen to this box? Then when it has traveled certain distance, this will come to rest. Okay, of certain distance, this will come to rest, which means the velocity of the belt and the velocity of the particular box will be the same. Okay, so it would have gained 2 meter per second with respect to the ground. Therefore, those two things will just move in aligned with each other. Okay, in that situation, obviously there wouldn't be any friction. So until that, this 2 meter per second speed has to go to 0 with respect to the belt. Okay, so initially it was traveling backwards with the speed of 2 meter per second. Then after some time, it reached the same velocity of the belt. Therefore, it will stay in the same position with respect to the belt. Okay, so with respect to the belt, after some time, its velocity becomes final velocity becomes 0. Okay, so final velocity becomes 0. So now it is pretty easy for us to say, for us to solve. So here, if you look at this sum, it is clear the initial velocity was like negative 2 meter per second and the final velocity was like 0. Then the only stuff that is missing over here is the acceleration. So acceleration, to stop this motion of that particular box, the acceleration was given by the frictional force. Okay, so frictional force, if I just get the acceleration from that frictional force, that will be the acceleration that is acting on this object. Okay, so now I have got the acceleration which is going to oppose the direction of motion. Okay, obviously then what I need to find here is actually the distance traveled by the box. Okay, so I just know the initial velocity, I know the final velocity, and then acceleration is something that I could get from the frictional force. What I need to find here is actually the distance that it has traveled, which means S. So what is the kinematic equation that I'll be able to choose? So the kinematic equation that I'm going to choose will be like the third kinematic equation which is like V square minus U square, that is equal to 2AS. So that's the equation that I'm going to choose. Okay, so next, if I do change this kinetic friction into mu mg. So mu is something that they've given over there. Mass will be the mass of that particular box with which it has been dropped. I do not want to know the mass because the acceleration is something that I need to get. So mass will get cancelled out. Yeah, g will be the acceleration due to gravity, right? So g could be taken as 10 meter per second square. They've given in the question itself. So you will have something like this: m, mass, acceleration that is being experienced by this box inside the reference of the conveyor belt, which will be equal to mu will be like 0.5, m will get cancelled out, and then you will have like one more 10 to it. So when you do cancel out these two things, m, you will have acceleration to be like 5 meter per second square. Okay, so now I have got the acceleration to be equal to 5 meter per second square. Okay, so this part is done. So next, I'll just put it into the kinematic equation, third kinematic equation. I'll get the answer straight away. Okay, so the third kinematic equation is v square minus u square, which will be equal to 2as. So the initial velocity was like, final velocity is like 0, so that stuff is done. So the initial velocity was like negative 2 meter per second. Okay, so negative of negative 2 the whole square, which will be equal to 2. How does the acceleration act on this particular object? The acceleration was actually acting forward in the positive x-axis. Therefore, that will be taken as positive itself. So let me put it as positive term, which is like 5 meter per second square in this situation. And then you have got the distance traveled, which is something that I need to find. Okay, so before coming to rest with respect to the conveyor belt, what would be the distance that it has moved backwards? That's what I need to find here. So the answer will be negative. Okay, so if I do solve this one, you will have like negative 4, which will be equal to 10. Yeah, right. And then s, so s will be equal to negative of 0.4 meter. So it is pretty obvious. From the position where it has dropped on the rope, it would have moved certain distance backwards and then it would come to stop. Okay, so if that's the case, then obviously the distance traveled by it will be negative direction. Okay, here I just put the acceleration of the conveyor belt in the forward direction. Okay, and the velocity to be negative, and what I need to find here is the distance s that was unknown. Obviously the distance s would have been in the backward direction from the position where it has been dropped. Therefore I just got the negative sign over here. Okay, s is something I just took it as positive. I do not know the direction, but it came out to be negative, which means the distance that it has traveled was in the negative direction, opposite to the direction of the force given by the conveyor belt. Okay, frictional force given by the conveyor belt and that surface. Okay, so you shouldn't have any doubt in this sum. So it has traveled a distance of 0.4 meters backwards. So instead of putting negative sign, is just the convention based on the direction that I've chosen over here. But the thing is, they're just asking us to find the distance. Okay, how far it has moved. Therefore I can mark the answer in positive itself, which is like 0.4 meter. Okay, so you shouldn't have any doubt in the sum. It should be clear. Fine. So solving the sum is actually an easy step over here. The thing is, you need to have an imagination of what's happening. Okay. So I put a box inside a belt which was moving with the velocity 0 with respect to the ground. If that was the case, then how would the box look for someone who is looking from the inside frame of reference? Okay. So how would it actually look? It will seem to be moving backwards. Okay. So that's the intuition that you need to know, because the entire system was moving forward. Okay, I just put a box that was with a velocity of 0 from the ground, so it needs to reach that 2 meter per second forward. Then what will happen to that box? It will just move certain distance backward, and then because of that frictional force, it will gain that proper velocity after some time, and then it will move with that constant velocity of 2 meter per second. Okay, so that's how it's going to be, right? You should be clear with all those things that I've told you. So this is little bit tricky while considering the imaginary stuff that we are doing, but the thing is, solving part is actually easy. Okay, so you shouldn't have any doubt on the sum. Let's move on to the next one. Next sum is something that we have already seen in the theory part. Okay, so what I will do is I'll just mark the option straight away. Fine. So I'll explain the question one time and I'll get the answer straight away. Fine. If you're just thorough with the theory, you will be able to get this sum. Okay. A block of mass m is in contact with the chord C as shown in the figure. Okay, so you're having a mass m which is just barely in contact with this chord C, which is going to travel towards the right with an acceleration alpha. Okay, so that's the condition over here. Okay, we have seen the same condition in the fictitious force. Okay, it was like case 3, same thing. The coefficient of static friction between the block and the cart is mu. So the friction that you are going to have between the block and this cart is actually mu. So that friction force is going to balance the mg if the acceleration alpha is good enough to balance it. Okay. So the acceleration alpha of the cart that will prevent the block from falling satisfies, which means at what acceleration this cart should move so that this mass that is barely sticking to the front side of the cart shouldn't fall down. So what should be the acceleration with which this cart should move so that this mass that is sticking to the front side doesn't fall down? Okay, so that's what I need to find over here. We have done this as a case 3 in the fictitious force in the theory part itself. So if you're thorough with that one, you should be able to get the answer straight away. Okay, so that was the formula that I actually found it over there. Same fictitious force and all those things will act. Okay, so you'll have the normal reaction, something like this, and then you will have like m alpha. Because of this normal reaction, you will end up getting a frictional force that will act upwards. Mg will be like downwards. That frictional force is going to balance this mass. Okay, so all those same logic idea behind it. So if the acceleration was greater than or equal to g divided by mu s, where s is the static friction, in this situation they have just given us the mu, therefore I could take it straight away for static friction. Therefore acceleration a should be greater than or equal to g divided by mu s or mu. So acceleration here is like alpha, so alpha should be greater than or equal to g divided by mu. Okay, so that's the answer for this question. You shouldn't have doubt on the sum. Let's move on to the next one. This sum is also simple one. Let's see. A block B is pushed momentarily along a horizontal surface with an initial velocity v. Okay, so you're going to push a block with an velocity v. Fine. Okay. If mu is the coefficient of sliding friction between the block B and the surface, the block B will come to rest after some time, after a time. Okay, so I just need to find the time over here. So I should get the time at what time this block will come to rest. Okay, so you are having a block that was pushed initially with a velocity v. So initial velocity is given, so the final velocity is something at which the block comes to 0. Okay, so that will be the initial velocity. So the final velocity of this block has to be 0. So if that was the case, at what time will it come to 0? Okay, so obviously I'll have to use the kinematic equation. The first kinematic equation will be good enough, right? So the initial velocity is like v, the final velocity will be like 0. I need to get the time t, so the only parameter that is left is actually the acceleration, right? So obviously if I need to get the acceleration, I just need to know the force that is acting over here. The force that is actually getting generated between these two surfaces is the kinetic friction. Okay, so because of that one, you will have like frictional force that is acting between these two surfaces. So this sum is the same sum as that of the conveyor belt sum, but in that situation it was like I'm just going to place a box on that belt. Okay, so everything was like flipped stuff. Okay, so you just looked at that case as a reverse case scenario, something like that. You just looked at it of other way around situation, which means when you look at that mass, Even though the mass was at rest with respect to the ground, it seems to be moving backwards with respect to the conveyor belt. But in this situation, it is just straight away sum, which means you are going to place a block on a surface. Okay, that block is going to travel forward with the velocity of v, and then it has to come to rest. Because of what it is going to come to rest? Because of the frictional force, it is going to come to rest. Okay, so that's it, right? So everything is just straight away. What if you do not want to know about the two frames of reference and you will have to study it? Just one frame of reference with respect to the earth itself, I'll get the answer. Okay, so simple, easy sum. Got it? So if Fk is the frictional force, then what will be the force that is acting? It will be equal to mu, and then you have like mg, right? So here, if I want to get the acceleration a that is acting on that object, you'll have like a, which will be equal to mu g. Just remove the m, you'll get the acceleration a, right? So that will be acting towards the left. Okay, if I plug it in the first kinematic equation, v equals u plus at, I'll get the answer. The initial velocity was like v, which was equal, the final velocity was like 0, which was equal to the initial velocity v, plus acceleration was opposite to it. Then you'll have like minus mu g into time t. So time t is something that I need to find. If I just rearrange it, you'll have like t, which will be equal to v divided by mu g. Okay, so v divided by g mu, that's going to be option 4, right? So this sum should be clear. It is easy sum, you shouldn't have any doubt. Let's move on to the next one. Next sum is the coefficient of static friction mu s between a block A of mass 2 kg and the table as shown in the figure is 0.2. Okay, so the coefficient of friction between this block and then the surface is like 0.2. Got it? Okay. What would be the maximum mass value of block B so that the two blocks do not move? So what would be the maximum mass that I could actually hang it over here so that this tension is good enough to balance that mass? Okay, so the entire system shouldn't move. If that was the case, what will be the maximum amount of mass that I'll be able to hang it over there? Okay, that is something that I need to find. The string and the pulley are assumed to be smooth and then massless, which means I do not want to worry about the mass of the string or the pulley. Okay, so everything is done. Okay, so you are having a 2 kg mass over here. Here this entire system isn't going to accelerate, therefore acceleration a will be equal to 0. So that thing is done. Okay, let me do the free body diagram for those two masses. So here, so with respect to the mass B, you'll have like tension that is acting upward, that is going to exactly balance the mass B. Okay, so mass B is something that I need to find, right? So mbg will be the force that this one is experiencing downwards because of gravity. Okay, so these two stuff is done. So then I'll go to the mass A. So you will have a tension that's going to pull this one towards the right, and then you will have friction that is acting opposite. F will be acting opposite to it. Okay, so that will be like static friction. Fine. And then the normal one. Okay, the normal reaction one. So you will have like normal that is acting upwards. 2g will be like downwards. Okay, so because that's like 2 kg, therefore 2g will be like downwards. Okay, so now I'm just done with the free body diagram of those two masses. If I just equate it, I'll end up getting the answer. First, let me put it for the mass 2 kg. You will have summation of force along the x should be equal to 0 because you do not want to have any acceleration. Okay, so that's 0. So you will have like tension T that is towards the right, and then negative of mu mg. They have given the mu to be like 0.2, so you'll have like 0.2. Okay, mass will be like 2g. Okay, mu mg, which is like 2g, that will be equal to 0. Okay, so if I do the rearrangement thing, so T will be equal to 0.4, right? So 0.4 g. Yeah, that's done. 0.4 g. So tension in the string will be equal to 0.4 g. So that stuff is done. So then same way I'll have to find the mass B. Okay, so I'll do the same force balance stuff for the mass B. You will have summation of forces along the y to be 0, summation of forces along the y to be 0 for the mass B case. So if I solve it, you'll have like tension in the T that's acting upwards minus mbg, which will be equal to 0. So T will be equal to mbg. Okay, so if I do equate these two stuff, I'll end up getting the answer. Therefore mbg, which will be equal to 0.4 g. Okay, so when those two stuff get cancelled out, you'll have like mb, that will be equal to 0.4 kg. So that will be my answer. The answer here is option 4, right? So gg will get cancelled out, right? So you shouldn't have any doubt in the sum. This is like pretty easy sum. Okay, let's move on to the next one. Next sum is a block of mass 10 kg placed on a rough horizontal surface having coefficient of friction mu which is equal to 0.5. Okay, so you're having a block which has a mass of 10 kg, it is placed on a horizontal surface, the coefficient of friction is equal to 0.5. So that thing is done. If a horizontal force of 100 Newton is acting on it, then the acceleration of the block will be, so with what acceleration it's going to move. Okay, simple sum. So you're just going to have a block on a surface. Fine, so the mass is like 10 kg, so obviously 10g will be acting downwards. You're going to have a normal reaction. Then the coefficient of friction between those two surfaces is like mu, which is like 0.5. So you will have frictional force that is acting backwards with the speed of with like mu mg, right? So that will be like 0.5 mg will be like into 10g. Okay, so that will be the frictional force that is acting backwards. And then if a horizontal force of 100 Newton is acting on it, then the acceleration of the block is, so you are going to have a pull over here that is going to be like 100 Newton. Okay, so it's done. So if the frictional force is good enough, then in that situation the block will be at rest, so it will get balanced. Now let me get what will be the maximum friction that is possible to give in the situation. So it will be like 0.5 half into 100, that's going to be like 50 Newton. So 50 Newton will be the maximum friction force that is possible over here to give. So it will balance like 50 of this 100 Newton. Therefore with leftover acceleration, with leftover force, it is going to travel forward. Okay, so when you do balance those things, the force that will be left will be like 50 Newton. I'm just doing it quick, you should get this stuff. What they're asking us to find is the acceleration, therefore it will be like m times a, so you'll have like 10 times a, so the acceleration will be like 5 meter per second square. The answer here is option 2, right? Easy sum, you shouldn't have any confusion. Let's move on to the next one. This sum is also based on the fictitious forces. Let's see what the sum is. On the horizontal surface of a truck, a block of mass 1 kg is placed, mu equals 0.6. Okay, so you are just going to place a block on a truck. Okay, so the first condition case that we saw. Okay, we will use that one. And truck is moving with an acceleration of 5 meter per second square. Then the frictional force on the block will be, so what will be the frictional force that is acting on that particular block? That's what I need to get over here. Okay, so let me draw a truck. You are just having a truck that is going to be accelerated with an acceleration of, that is going to get accelerated with an acceleration of 5 meter per second square. Okay, so if that was the case, you are going to have a load inside a truck. Okay, so you are having a block of mass 1 kg. So what will be the effect on that mass? It is going to move opposite to that of this acceleration. Okay, same case that we did see in the conveyor belt, same thing over here. It will have the exact opposite effect of something that is happening externally. Okay, so this one will experience the same acceleration in opposite direction. So you will have the acceleration a 5 meter per second square opposite to it. Okay, so then the frictional force on the block will be, so what will be the frictional force that is acting on this block? That's what I need to get over here. So if you do the free body diagram, you'll end up getting the answer straight away. Okay, so you will have a force of ma that is acting backwards, and then you will have a frictional force that is going to act the other way around to balance this block. Okay, if the frictional force is good enough, then this will not move, it will balance the block. Okay, so frictional force will act towards the right in this case. Obviously he will have normal reaction that will be upwards and mg that will be like downwards. Okay, so what they're asking us to find over here is the frictional force on the block will be, if the frictional force is good enough on this mass, then this mass will not get accelerated backwards. Okay, first let me get the maximum frictional force that is possible in this situation. Fk will be equal to mu mg, right? Instead of mu, I'll substitute like 0.6. For mass, I'll put in 1, and then for g, I'll just substitute like, yeah, I'll just put in 10. Okay, so the maximum frictional force that is possible over here is actually 6 Newton. Okay, So 6 Newton is possible. So with what acceleration will it move? Will it try to move backwards? It will try to move backwards with the force of 1. Here if I just plug it over here, you will have 1 into 10. Yeah. So 1 kg, right? So 1 into 5. It's not 10, it is like 5 meter per second square, right? Therefore 1 into 5, so it just it will experience a force backwards inside the truck with the force of 5 newton. Okay, so the maximum frictional force that is possible over there for me to give is actually 6 newton. Obviously, then this is the maximum kinetic friction that is possible over there, or static friction that is possible over there. Okay, so if that was the case, only if it crosses the 6 newton barrier, it will be able to move. Okay, so that is when like kinetic friction will come into picture. But in this situation, it didn't even cross that mu. Okay, that 6 newton break even point. Therefore, obviously this mass isn't going to slide backwards. It will be at rest because frictional force has actually balanced that MA that has been generated by fictitious force. Okay, so those two stuff is actually balanced. Therefore, this is not going to move. So if it will not give like extra force, friction force will just balance the opposing effect. Therefore, the force that is going to act on this object will be like 5 newton. The maximum frictional force that is possible is like 6 newton, but in this situation we do not want to generate 6 newton force because the opposing force that has been generated over here is just 5 newton, so it will give 5 newton to balance that 5 newton opposing force. Okay, so the answer here is option 1, right? You should be clear with this sum, you shouldn't have any confusion. It's an easy one. Let's move on to the next one. Next sum is little bit tricky. Let's see what the sum is. A block of mass 10 kg is in contact against the inner wall of a hollow cylinder drum of radius 1 meter. Okay, so you're having a block which is like 10 kg that is inside a hollow cylinder, fine, and the radius of that particular cylinder is actually 1 meter. Okay, so it is in contact with that inner wall, which means it is sticking to the inner wall. Okay, so it is just in contact, fine. The coefficient of friction between the block and the inner wall of the cylinder is 0.1. So they have given us the coefficient of friction between the wall and then the block. Okay, that is like 0.1. Fine. The minimum angular velocity needed for the cylinder to keep the block stationary when the cylinder is vertical and rotating about its axis. Okay, so this block is actually kind of sticking to that inner wall and the entire cylinder is actually spinning. Okay, so if that was the case, with what angular velocity it should spin so that the block is still sticking to the inner wall of that cylinder without falling down. Okay, so this is a kind of same situation as we have seen in the case 3 scenario when an cart was moving forward and there was a block that is just in contact on the front side of that particular cart. Okay, this is kind of the same scenario over here, but the stuff is here it is just spinning. Okay, so that's the difference over there. Okay, so here you will have like centripetal force that is actually acting. Okay, there it was like the acceleration, here you are having that spinning, so you are going to generate a centripetal force. Because of that centripetal force you will have fictitious force acting on that particular mass, which we will call it as centrifugal. Okay, so I'll get used to it. While doing this sum, I'll just give you the idea how does it actually match with that cart sum that we have seen already in the case 3 of the fictitious forces. Okay, so I'll do the matching, you'll get it. So here the imaginary stuff seems to be a little bit difficult, but we'll do this kind of sum more often in the upcoming chapter, so I'll get used to this kind of logic also. Okay, so what I need to find here is actually the minimum angular velocity with which the cylinder needs to spin, which means I just need to get the omega. Fine, so the unit seems to be pretty clear, it is like radian per second. So with what angular velocity it should spin so that the block that is sticking to the inner wall of the cylinder doesn't fall down. Okay, I think you're clear with the question. Now let me draw the diagram for that particular question, so I'll get much more clear picture of what the question actually is. Okay, so you are having a cylindrical drum. Got it? You are just having a drum. This is like a cylindrical drum. This is going to spin about the axis. Okay, so this drum is going to spin about the axis with an angular velocity omega. Fine, you are having a block that is actually in contact with the inner wall of that particular cylinder. Fine, so you are having a block of mass 10 kg that is in contact with the inner wall of that cylinder. So this block has to be in contact so that what will be the angular velocity that I need to get. Okay, so that's what I need to find over here, right? So here the imagination is, so this is the imagination that you need to know. So whenever an object is going to spin in a circular path, what I need to give is the centripetal force. Okay, so centripetal force is something that I need to give. That is one that will move in a circular path. We have already seen in the last chapter itself, when if you just given velocity to it, what will happen is it will just move in a straight line. Okay, so if I just keep on pulling it inwards, what will happen to it with the correct force, then it will move in a circular path. Okay, so that is what is meant by centripetal path, centripetal force. Okay, so here in this situation, this entire drum is actually moving in a circular path. Okay, so if we just pick an arbitrarily any point in this drum, this mass is going to move in the circular path, because I've just connected it to a rotor, and then it is fixed on an axis. Okay, so that axis is actually pulling this entire mass towards the center. Okay, therefore this is moving in a circular path. Okay, so you are having a centripetal force. I'm just giving a centripetal force because of this from that axis. Okay, so that axis is actually pulling all those masses inwards, therefore, and also I'm just giving an horizontal velocity to it with respect to the tangential velocity, therefore it is moving in that entire cylindrical drum is moving in a circular path. Okay, in a rotational motion. So same thing is happening over here. Okay, so every object, mass that is on this periphery of this drum is actually experiencing a centripetal force, and then it had an tangential velocity, therefore this is moving in a circular path. Okay, so that's the notion. So if that's the case, for someone who is standing inside this drum and looking at this object, what will happen? What will happen to this object? This object will arbitrarily experience an opposite force to that of the external cause. Okay, so externally I'm just pushing it in so that it is moving in circular path. Okay, so then what will happen to this mass which is internally available in this drum? What will happen to that particular mass? This mass want to move outwards. Okay, so that's the notion that you need to know. Okay, so when the truck was moving forward, the object that is inside was actually trying to move backwards. Okay, so the same thing is going to happen here. The centripetal force that is required for this particular mass to move in a circular path will be given by this drum. Okay, so in turn what it will do is it just wants to come and stick to the periphery of this drum, which means it just wants to break this drum. Okay, so it will experience a force that is opposite to that of the external force given by the drum. Okay, so that's the intuition, right? So in the previous cases it was easy for us to imagine because it was like a linear motion, but in the situation it is like a circular stuff. Okay, so if I am just giving a centripetal force from the external frame of reference in the internal frame of reference, which means inside that system that entire object wants to move radially outward. Okay, so that would be the case. Okay, so it will be like flipped of the effect that is happening outside. Okay, so that's the intuition that you need to know. So if I just look at this mass, okay, it just needs to stick to the wall so that it doesn't fall down. Okay, so if that was the case, obviously the frictional force has to balance this mass from falling down. So why does the frictional force got generated? The frictional force got generated because of the fictitious force that is acting on that mass. Okay, so that fictitious force will be opposite to that of the external cause. So externally I just gave the force inwards to move it in a circular path. In the situation, the object that is internally will experience the same amount of acceleration outwards. Okay, with respect to that particular mass, I'll get the force that is being experienced by that object inside the frame of reference of the drum. Okay, you should get this notion clearly. Okay, just do the imagination same as you did it for the translational motion with the case of fictitious forces that we studied. Okay, it should be clear. Okay, same idea, same notion, whatever that is happening outside, if you look at from the inside frame of reference, that it will look like other way around. That's the intuition that you need to know. Okay, so here now I'm just ready to do the force balance stuff over here. So the force balance will be like frictional force that will be upwards. Okay, so frictional force has to balance this one. In turn you will have like mg that is going to act downwards, that will be like 10 kg, therefore that will be like 10 g. Okay, so this entire system, this entire block that is inside this system wishes to come out by an acceleration of v square by r. So that is what is meant by centrifugal force. Centrifugal force actually means you're just going to look at that object from inside the frame of reference. Okay, from outside I'll have to push it in. For someone who is looking at it from the inside, that particular point wants to move out. right? So that is called as fictitious force. Obviously, for circular motion, I'll call that fictitious force as centrifugal force. Okay, so do not worry about that particular term. But the stuff that you need to know is when you are going to look it from the inside frame of reference, I'll call it as centrifugal force or the fictitious force. Okay, so in this situation, as it is in rotational motion, I'll call it as centrifugal force. Okay. Anyway, let us use the same convention, which is like fictitious force. When you look at from the outside, I'm just giving force internally, or I'm accelerating it inside, radially inward. So if I just have to look from the inside frame of reference, then that particular block would have gained an acceleration radially outward. Okay, those who are counterintuitive thinking, you should get this stuff right. Okay, so here this particular mass experienced and radially outward acceleration, which will be equal to, yeah, m v square by r. Okay, so because of this, that mv square by r radially outward acceleration, those two got squeezed, therefore this surface will give an inward force. So that's the centripetal force that is giving on that particular mass. Okay, so that will be the normal force in this situation. Okay, so the normal force over here is given by the surface between the drum and then the block, so that will be the normal force over here. Okay, so this was the normal force, right? So now I'm just done with the free body diagram of that particular block. So only confusing part over here is the direction towards which direction I should put the centric and the fictitious force. Okay, so fictitious force will always act opposite to that of the effect of the external condition. So when I look at from the external frame of reference, it seems to be pretty obvious. I'm just accelerating all those point radially inward. Then what will happen for someone who is looking from the inside? Because I'm just worried about that particular block, and then I'm looking at the block from the inside frame of reference. Okay, and then I just have to put all those forces. So the block that is situated internally has to come out by the same acceleration that I've given already inwards. Okay, so that's the counterintuitive thinking which you need to know. So now free body diagram is done. Just straight away solve it, you'll get the answer. Okay, so summation of forces along the x will be 0. So let me consider this to be my x and this will be my y, because mv square by r will be balanced by the normal reaction. This block isn't going to break the drum. Okay, so these two things will be these two things has to be balanced. So summation of forces along the x is 0. Same way, summation of forces along the y will also be 0. Okay, those two stuff will also get balanced. Okay, so if that's the case, then n, that will be like negative n. Okay, plus mv square by r will be equal to 0. Therefore, you will have normal reaction which will be equal to mv square by r. For summation of forces along the way to be 0, let us put it. So you will have F that is actually acting upwards, and then you will have like minus 10g which should be equal to 0. Okay, so instead of mu, I'll substitute like mu n minus 10g which was equal to 0. Okay, so what was the new that they have given in the question? It was like 0.1. Okay, so that's the coefficient of friction between the block and the inner wall. So you will have 0.1, n will be like mv square by r, right? So for mass, I'll put in 10 kg, so that's what they've given. All right, so yeah, it's like 10 kg. Therefore mv square by r, you'll have like 10 v square divided by r minus 10, yeah, minus 10 into the g. Okay, so acceleration due to gravity could be taken as 10 meter per second square. They have given in the question, so that will be like one more 10 to it, which will be equal to 0. Okay, so what I need to find here is not the velocity with which it needs to spin at that particular point. They're not asking us to find the linear velocity over here. What they're asking us to find is the angular velocity with which this entire drum has to spin. Okay, so according to this, according to this angular velocity, you will have the linear velocity at this required linear velocity at that part at this particular point. But the stuff that I need to find is actually the omega. So they have given us the radius already. So the relation between the v and then the linear velocity and the omega is actually v equals r omega, right? So you'll have like v that is equal to r omega. So if I do put that stuff straight away over here, you'll have like r omega the whole square. R will get cancelled out. right? So R will get cancelled out, then you will just be left with R omega square. Okay, so let me do the solving, you'll get the answer straight away. Yeah, rest all of the stuff are just the easy one. So you just had 0.1, or like 0.1 into 10 will be like 1, so let us leave that stuff. You had like R omega square, which was equal to negative of 100 goes to the right hand side, it becomes like 100, positive 100. So R was equal to 1 meter, right? So radius was equal to 1 meter. So omega square will be like 100. If I do take the root, I'll end up getting the answer to be like 10 radian per second square. Okay, so the answer over here is 10 radian per second square, which is like option 4, right? You shouldn't have any doubt in this sum, it should be clear, fine. So the only tricky part in this sum is the entire stuff is moving in a circular path. Okay, for the translational motion, which means for linear motion, we have already seen different cases in the theory part, but we didn't see for the rotational stuff. Okay, the rotational stuff is also same like that of the linear stuff. Whatever that we see from the outside, internally it is going to act opposite, the same logic. Okay, so from the outside perspective, I gave centripetal acceleration at every instant to make that particular object move in a circular path. Okay, if you just stay inside the object and look at any other object inside the particular frame of reference, okay, that circular motion thing. Okay, if you just look inside, if you just stand inside that object and look at any other particle inside that object, that entire particle will experience an opposite effect to that of the effect that is happening externally. Okay, externally we just pushed it in, then internally everything wants to come outside, radially outward. Okay, so that's the notion that you need to know, fine. So if you are just clear with that idea, so whatever it is, if whatever acceleration that is happening outside, you will have an exact opposite effect that will happen inside that frame of reference. Okay, so that's the notion that you need to know, fine. You shouldn't have any doubt on this sum. So this sum is a little bit tricky based on the imagination and logic. Okay, we'll get used to the same kind of intuitive thinking again and again in upcoming chapters, so we'll get used to it. Okay, so that's the thinking that you need to know, fine. Rest other solving are just the easy stuff. Okay, so you shouldn't have any doubt in the sum, it should be clear. Let's move on to the next one, fine. Next sum is one end of string of length L is connected to a particle of mass M. So you are having a mass that is attached to the string of length L, and the other end is connected to a small peg on a smooth horizontal surface on a table. Okay, so you're just having a frictionless table, and then one end is connected to a mass and the other end is actually fixed to a peg, which means it is just fixed. That will be the point about which it is going to rotate, fine. If the particle moves in a circle with speed v, so the entire particle is moving in a speed v, something like this. You are just having a table that's frictionless. Same way, you are just having a string. One end of the string is actually tied to a stone or a particle of mass m, and the other end is fixed, about which this stuff is going to rotate. Okay, so that's how it's going to be, right? If the particle moves in a circle with a speed v, so the velocity with which it is going to move is actually speed v. So it is going to move with a speed v. The net force on a particle is directed towards the center, obviously. So I'm just looking it from the outside frame of reference. Therefore, when I look at that particular particle, it will have it will have a force that is directed towards the center, which will be given by the tension in the string. Okay, the net force on the particle directed towards the center will be, so what will be the force that is needed on this particular object so that this object is going to move in a circular path? What will be the force that is needed? Someone has to pull it in. That is when it will move in the circular path, or else it will just move straight. Okay, it will just have a linear motion. If I just want to change the direction of the velocity, obviously I need to give the force. That force will be directed towards the center, which is called a centripetal force. Okay, if there is a guy who is standing inside this particular sphere, and then if he looks at any other particle inside that sphere, then in that situation that particle inside this mass will experience a radially outward force. Okay, other way around. Okay, you're just standing inside that frame of reference and then you're looking at that object. But here, for someone who is just standing outside and then he is looking at this particle which is moving in a circular path, if that was the case, then obviously this entire system will experience needed force that should be radially inward, which will be given by the tension in the rope. Okay, so what they're asking us to find is the net force on the particle will be, so what will be the force that is acting on this particular particle? So the force that I need to give on this particle to move on a circular path will be the centripetal force that will be given by the tension in the string. Okay, so T represents the tension in the string. So obviously this is a kind of easy straightforward sum. Do not want to think too much and all, right? So here I just have to pull it inward. If I give good enough force to pull it inward, it will just follow that particular circular path. If the force wasn't good enough, then the string will break. Okay, that's it. So here in this case, the force was good enough. So the entire force was given by the string in the way of tension in the string. Okay, therefore the answer here is option 4. Straightforward, simple sum. You shouldn't confuse the sum. Okay, don't get confused. This is just a straightforward application oriented sum. Okay, it should be clear. Let's move to the next one, which will be the final question for this particular session. Okay, this is just straightforward sum that we have seen already in the theory. Okay, we are just going to find the formula that we have already derived in the theory. Okay, so this is based on a car, motion of a car on a banked road. Okay, you have got a car is negotiating a curved road of radius capital R. Negotiating actually means it is moving. Fine, a car is negotiating a curved road of radius capital R. So it is moving in a curved road, which means motion of a car on a circular track. The road is banked at an angle theta, banked road. The coefficient of friction between the tire and the road is actually mu s. The maximum safe velocity on this road is, okay, so they're asking as the big formula that we have learned in motion of a car on a banked road. So that's what they're asking from us. So here you will have GR. So obviously option 4 should be the answer. It is like GR in the numerator, and then you'll have like mu s plus tangent theta divided by 1 minus mu s tangent theta, which is like option 4, right? This sum should be clear, right? So in this session, we did see sums that are related to tension and all those stuff. And the only extra concept that we saw was like the fictitious force in the case of circular motion. So that fictitious force is called a centrifugal force, okay? So these are something that you need to know. In the next session, we will do all those sums, leftover sums that are related to motion of car on a circular track and those stuff, okay? So you should be clear with all these 10 sums that we have seen in this session. With this, the video gets completed. Bye.